Yesterday we looked at question 1, question 2, as well as 3 and 4, and 7b, right? So today I'll start with all the other questions that we didn't do, and then if you guys want me to get back to some of the questions that we did yesterday, we can get back to them after, right? So let's look at question 5. Here we're given x, the limits as x tends to infinity of 5x squared minus sine 3x over x squared plus 10. So the way you can solve this is the way we solved 3 and 4 for those who were there yesterday. But basically what you have to use here is the squeezing theorem, right? Which you guys did in your notes, right? So, and the squeezing theorem is all about finding it's all about finding the limits of a function that we do know, and then use that to find the limits of a function that we don't know, right? And the reason why this squeezing theorem is particularly important for these type of questions is because, and I'm sure you guys will see when you do L'Hopital's rule, when you apply L'Hopital's rule to these problems, because when you substitute infinity here, you will have infinity over infinity, which is one of the conditions to apply L'Hopital's rule. But what you'll see and what you'll notice as you apply L'Hopital's rule is you will be able to eliminate, right? You'll be able to eliminate all the other terms here except the trigonometric terms. So you will always end up not being able to really get to a strict solution, right? Which is why the squeezing theorem is applicable here, because the squeezing theorem helps you to sort of narrow down the exact value of the limit. Well, in this case, the L'Hopital's rule for this particular problem wouldn't really help you get any closer to the solution, right? And when you guys do L'Hopital's rule, we can always come back to this, and you'll see exactly what I mean. Okay. So here, what we'll do is we'll start with the sine function, right? So we do know that sine minus 1 is less than or equal to sine of 3x, right? Which is less than or equal to 1, right? So we know this. We know this from our trigonometric identities, right? So sine and cosine of any angle are always and will always be between -1 and 1. And what I told the guys yesterday is if you have a calculator handy next to you, you could try it out and see that it does really work out that way. So try to type, for example, sine of 15,000 or 15 million, right? Any angle, the sine and the cosine should be between -1 and 1. So we know this. Please mute yourselves. We know this, okay? So now that we do know this, we'll try to get this function sine here, 3x, manipulates this whole thing inequality here to get something like the limits that we're trying to find. And the way we do that is, we can see that in the function we have minus sine 3x. So we multiply by -1 on all sides. And what happens to an inequality when you multiply or divide by a negative value? What happens? That's my question to you guys. Yeah, I see a hand raised. You don't have to raise your hand. You can just unmute yourself and speak up.
So it will change the inequality sign, whereas we'll have sine 3x where it should be it should be great. So it's great. Okay, it changes the inequality sign.
It changes the
It
inequality
changes the
sign, right?
inequality sign, right? Yeah.
Okay, so thank you. That's exactly right. So when you multiply by -1, the -1 here becomes 1. Then less than or equal to becomes greater than or equal, right? And then the sign becomes minus sign 3x. And then the less than also becomes here greater than or equal to -1 now. Okay. So now we've managed to get the the minus sign 3x there. So next, what we have to do is, because we have a 5x squared here, we have to substitute. No, we have to also add, we have to add 5x squared on all sides of this inequality. Now, here it's a bit tricky. That's where you need to determine if x is tending to positive infinity or negative infinity. Because, well, it really doesn't make a big difference in this case. But in a case where you had, for example, 5x cubed, if x tends to negative infinity, for example, the 5x cubes will be negative, meaning when you add it, well, it doesn't really change the sign of the inequality. But in the, let's say if you had x cubed in the denominator here, right? And when you had to divide by x cubed plus 10, you would have to change the sign of the inequality, because then if x tended to negative infinity, this whole thing here in the denominator would be tending to a negative value. So you would have to change the sign of the inequality for that. Okay. It's a bit more clear in the cases of 3 and 4. So I think I'll go back to one of those just to illustrate what I mean here. So let's add 5x squared, right? And let's say for our case, x is tending to positive infinity, right? So let's add 5x squared on all sides of the inequality. What do we have? We have 5x squared plus 1, right? And then in the middle, same thing, 5x squared plus, no, minus 1, right? And then on the right-hand side, 5x squared minus 1. And then we divide now. We can see that we're getting closer to the function that we want to get, right? So now we divide by x squared plus 10 on all sides. Again, since this is tending to positive infinity and it's the square there, you will see that whatever we dividing in the denominator here is a positive value. So we really don't have to change the sign of the inequality, right? So let's divide by x squared plus 10. Here too, let's divide by x squared plus 10. And here as well, let's divide by x squared plus x squared plus 10. Okay, so now another way, because an inequality usually, and I'm sure you guys remember this from high school, usually you wouldn't want to have an inequality written like this. You would want it to be in the standard form where you have the less than, right, inequality rather than the greater than. So the way you can convert this or sort of move things around is you could do this, right? All you do is you take this to the left hand side and you take this to the right hand side. So it would become, and then here you have now, and here you have now So these two inequalities are equivalent, so they are basically the same. So what we've done here, we've basically identified the range between which this function exists, the range of values, right? So now for our specific case, we have that the limit is tending to positive infinity. So what the squeezing theorem tells you is if you find the limits of either of the two functions that are at the extremities here, you will be able to easily find or easily estimate the limit of the function which is in the middle, right? Which is what you want to do, right? So what you do is you just try now to determine the limits, right, of the functions. Let's take first the function that is on the left-hand side here. So 5x squared minus 1 over x and squared plus 10. Again, since x squared is the highest degree in the numerator and denominator, you divide by x squared everywhere, right? Which is, I'm sure, what you guys did with Dr. Mshlongo. So this is the way I'll do it, just to sort of simplify your understanding. You divide by x squared in the numerator as well as in the denominator. Right, so let's do that. Right, and then what happens is we can simplify then this to be the limit of 5x, 5, sorry, minus 1 divided by x squared divided by 1 plus 10 divided by x squared. And now when you substitute in the value of x, which is infinity, you have in the numerator 5 minus 1 over infinity, which is 0. So basically in the numerator, you have 5. And in the denominator, you have 1 plus 10 over infinity, which is 0. So 1 plus 0, which is 1. So you have 5 over 1, which is 1, which is just 5. So our first limit is equal to 5. So now let's find our second limit. So our second limit is of the function that's on the right-hand side now. So let's do the same. This will be equal to, again, x squared is the highest degree on both the numerator and the denominator. So you divide by x squared everywhere. And what you get is this, right? And then again, when you substitute the value of x as it tends to positive infinity, you have 5 plus 0, which is 5, divided by 1 plus 0, which is 1. So 5 over 1 is just 5, right? And that is it. So the two limits are equal. So basically, the limit of the function that is in the middle here is just equal to 5 based on this inequality, right? So that's what you conclude. So now you conclude that, right? Therefore, please mute yourselves. So therefore, you can conclude, therefore, by the squeezing theorem, the limit as x tends to positive infinity of x squared or 5x squared minus sine 3 over x squared plus 10 is just equal to 5, right? So that is it. So basically that's what you will be doing for the other problems, okay? So let's do another one, just sort of cement this understanding. I see a hand raised. You can mute yourself and ask your question.
So say I have a question. What if the
Mm.
answers answer the same?
Well, what you will see now is especially for the squeezing theorem. So as I said, the squeezing theorem is really applied for the functions that are not easily solved using L'Hopital's rule, because as soon as you guys do L'Hopital's rule, you will really understand this concept. Is L'Hopital's rule is a lot easier to implement when you've done the differentiation, because L'Hopital's rule uses the differentiation, right? And with L'Hopital's rule, it's usually you just have to derive the numerator and then divide it by the derivative of the denominator, and then you just implement the limit again, right? So you do that until you get an answer. And with L'Hopital's rule, it's after a few, I think maximum of like three, 4 derivations, you should get to an answer, right? But now for functions like this, right? Question 3, question 4, question 5, and question 6. L'Hopital's rule is a bit tricky here because you have trigonometric functions, and trigonometric functions, they don't disappear when you when you do when you take the derivatives, right? So when you derive sine, it goes to cosine. When you derive cosine, it goes to minus sine. So they keep going around. So they will never really um, simplify in such a way that when you substitute the limits, right, as x tends to infinity, you get a specific value. So it will always be sort of ambiguous, or rather, it will be hard to 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 get to a specific value, right, for this type of functions if you apply L'Hopital's rule. But now, for all of the functions that you will be using, you'll be using when you apply the squeezing theorem, you should be able to get the same limits on both sides, right? You should be able to get the same limits. I have not come across an example um, where you get different limits on either sides of the inequality, right? But don't take my word for it, okay? You can look it up as well, just as homework, or as for your own information. You can look up the squeezing theorem and you can see if there's any case where it comes up as two different values and what they do in those cases, okay? So you can try and look it up as well for your own information. But so far, I can tell you, I've never come across a case like that, especially for you guys who are doing first year mathematics. You don't, well, they make it a bit easier, right? So you don't have to go to those extreme kind of cases if they exist. Okay, so really what I'm saying is I don't know if if it ever happens, but I've never come across that kind of cases. Okay, right. So moving on to
Before we continue, sir,
yeah,
if we have different, or like in the case, you see the other question, we have cos and sine.
yeah,
So do
this
we
one
also
here,
use the same method?
same method. Yes,
Okay,
we'll
thank
do
you.
it just now. This one here, it's talking about question 6.
Yes, I'm talking about question 6.
Yeah, we'll do it just now so you can see. So basically what we said again, for sine and cosine, right? The values are between -1 and 1, right? So this applies for both sine and cosine. So in this case, we have both sine and cosine, so let's just write them down. But now you can see here that we have cos cubed of x, right? So as you take the cube, so now you have to take the cube on all sides. And what happens when you take the cube of negative value? So when you take -1 cubed, it just stays -1. And then in the middle here, right? In the middle here, you have cos cubed. And then on the right hand side, and again, it's 1 cubed, which is just 1, right? And then now you see that you have sine x plus cos cubed. So you add these two, you add these two inequalities, right? When you add them up, what does that become, right? So when you add in, let me just write here 2, and then right there 1, and then let me say by adding up 1 and 2, we get the following. So look at the left hand side. On the left hand side, you have -1 plus -1, which is -2. In the middle, you have cos cubed plus sine, which is just sine x plus cos cubed of x. And then on the right hand side, you have 1 plus 1, which is 2, right? And then what we see here also is we have x squared, right? So now we have to look at the sign of x, right? We can see that x is tending to negative infinity, so we have to pay attention here. But now in our case, when we multiply by x squared on all sides of the inequality, do we change the sign of the inequality or do we keep it the same? I'm asking you guys.
It has to remain the same since since the sign is positive.
Yes, since it's x squared, so it's minus infinity squared, which becomes positive infinity. So it has to stay the same. So let's multiply by x squared on all sides. Right, so multiplied by x squared here. And multiplied by x squared there, you have 2x squared. Right? And then when we divide by x squared plus 1, do we change the sign of the inequality or not? Again, I'm asking you. Guys, do we change the sign of the inequality?
Remains the same.
Remains the same, thank you. So let's divide by x squared plus 1. Please, when you're done speaking, you can mute yourself so there's no interfering sound in the background. Right, so you have 2x squared divided by x squared plus 1. Right? So now we have to divide by x minus 3. Should we change the sign of the inequality or not when we do that?
No.
Anyone else?
No.
So we shouldn't change the sign of the inequality. Can you explain why? And really try to think about it.
We do change it.
We do change it. Why?
If we'd insert negative infinity to x, we'd get a negative infinity instead of positive infinity, so we do change it.
Right, because we're dividing by a negative value, right?
Negative.
So
Yes.
now it becomes greater than here and greater than there. And we divide by x minus 3 here and x minus 3 there, as well as x minus 3 here, right? So again,
Sorry, sir.
yes.
Sir,
Mhm.
sorry. Can you please I'm kinda I can't comprehend why the signs are changing. Can you please like go through that? Because
Yes.
I didn't hear him. Yeah.
Okay, so I'll give an example, which is a simple example that I gave yesterday. Let's say we have something like, I'll just put in numbers, right? We know that -1 is less than, for example, -1 is less than 5, right? Which is less than, let's say, 6, right? This is true. So now let's say you divide by -1 on all sides. What do you get? And let's say you keep the sign as is, right? So let's try to keep the sign as is, and then we see what we get. So dividing by -1 on the left-hand side, you would get -1 divided by -1, which becomes 1, right? Divided by -1 in the middle, it's 5 divided by -1, which becomes -5. On the right-hand side, 6 divided by -1, which is -6. Now, does this make sense like this? Is 1 less than -5?
Like sir, look, I understand like the nature behind dividing by like negative, that the sign changes. What I'm
Yeah.
asking is, we right up there, we are dividing by x minus 3, right?
Yeah.
I'm asking, why are the sign changing?
The sign of the
Is it
inequality.
yes.
Yes, same logic
Why? Same logic as
as this one
the
here,
one
the
you
one I
just
just did.
portrayed.
Yes, because x minus, remember, x in our case is tending to negative infinity, meaning when you substitute x into this, it's minus infinity, right? So it's a very it's a negative number, basically. And remember, as I just illustrated here, when you do divide by a negative number, you have to change the sign of the inequality for it to make sense. Otherwise, it doesn't make sense as an inequality. Right?
Right. Yeah.
You
Got it.
understand now?
Yeah.
Okay. Anyone else? Any other questions? Okay. So now you can rewrite this inequality. So it's because, as I said, it's always better to leave it as less than and less than here, which is what you guys are used to from high school. So you just have to switch, take what's in on the left-hand side to the right-hand side. So here it becomes plus, and take what is on the right-hand side to the left-hand side, right? And that now is your final form, right? So what you have to do now is you have to take this limit and implement it on either on all sides of the inequality, right? So let's say we apply it for our first case here. What is that equal to? Well, this is equal to, again, in the numerator now. Let's try to expand the denominator first. So you guys can see what I mean. So I don't skip a step. Let's expand the denominator. We really don't have to, but it's just for clarity purposes. So let's multiply, and we have x squared times x, which is x cubed, x squared times minus 3, which is minus 3x squared, 1 times x, which is just x, that's x, and then 1 times minus 3, which is just minus 3, right? So in our case, again, x cubed is the highest degree in both the numerator and denominator. So what you do is you divide by x cubed everywhere. So let's divide by x cubed in the numerator as well as in the denominator. So you didn't have to expand this, but I just did it to show you guys which term in x was the highest degree. But you could have easily seen that it's x cubed as well if you just looked at the x squared multiplied by the x here. That's the highest degree, so you have to divide by x cubed everywhere. Now, when you simplify this, you should have, in the numerator, you should have 2 divided by x. In the denominator, you should have 1 minus 3 divided by x plus x divided plus 1, sorry, divided by x squared minus 3 divided by x cubed, right? When you substitute in the value of x now, you have 2 over x, which is 0, divided by 1 minus 3 over x, which is 0, 1 over x squared 0, same as minus 3 over x cubed, right? So it's basically 0 divided by 1, which is just 0. So if you apply this to the right-hand side of the inequality, which is just a minus with a minus there, you should be able to get the same answer as 0, right? And then basically your conclusion now will be, remember that's the question that we're trying to solve, the limit as x tends to negative infinity of this whole thing here, therefore also has to be 0. And that's done, right? Any questions there? Any questions, anything at all? All right.
Before the end of this session, can you please show us how to use the other theorem? I think you said P something.
L'Hopital's rule.
Yes, the L'Hopital's rules.
We'll do that next week. That's what I said. Since you guys haven't done it in the notes, you guys haven't done it in class, right? It's in your syllabus, so you will have to study it at some point. And I'm sure you guys will do it. If not next week, probably the week after that. So whenever you guys do it, we'll have a session where we look at at L'Hopital's rule, problems involving L'Hopital's rule. And you will see that you really need to know your differentiation because you will be using derivatives for L'Hopital's rule a lot. So you need to become familiar with all those derivation rules. Okay, which is what I want to do now. So let's do differentiation. Let's look at sub question A. So we asked to perform the differentiation of ln of x cubed times cos x over root of 1 plus 3x, right? So now the rule, okay, if you guys don't have this rule, you can write it down. When you're looking for the derivative of ln x, okay, when you're looking for the derivative, and from now on, just for reference, I'll be writing derivative as this little sort of apostrophe like that, okay? And which is what you guys will do as well in class. So just remember that. So this basically means the derivative of ln x. Oh, let's make it in general the derivative of a function ln of fx. What you do is you take the derivative of the inside function, right, which is just f of x. So you take f prime of x, right, which is just the derivative of x, divided by f of x. So that is the rule. Okay, so now for example, this is in your notes, but I just want us to sort of practice this. Let's say, for example, you now had to find the derivative of ln x. You apply the same formula. So this is more like the general formula, right? For any sort of function, it could be x, it could be x cubed, it could be the function like the one that we have in sub question A here, which is why I always like to tell people to just, if you just know the general function, you can apply it to any function. So let's say we're looking at ln of x. You have to take the derivative first of x. What's the derivative of x here? Guys, you've done derivatives. I know you have. So what's the derivative of x? You've done at least the introduction. So you should know. It's 1, right? So 1 divided by f of x. In our case, f of x is just x. So 1 over x. So the derivative of ln of x is 1 over x. Now let's apply it to our case here. Here we have ln of this whole thing here. Let me just copy this and paste it there. Right, so we have this whole function here. And basically what we have to do now is find the derivative of that function divided by the same function. Right, if you apply the formula that we did get there. So what's the derivative? So really what we have to do is solve the numerator here. So what is the derivative of this whole thing here? Here, again, for this case, for example, you'll be using the chain rule of differentiation as well. You go from outside to, or rather you go from inside to outside. So let's look at the derivative here. Here you have a function divided by another function. So you have the quotient of two functions. And this is also one of the rules that you guys have. You have that when you're looking for the derivative of some function f of x divided by some other function g of x, right? What you do is you take the derivative of f of x, you multiply it by the function g of x, then you subtract f of x multiplied by the derivative of g of x, right? And then you divide all of that by the denominator squared, which is just our g of x squared. Right? So that is the quotient rule of differentiation. Okay, you guys should be familiar with this rule as well, right? It's called the quotient rule, and it should be in your notes. So really you have to really familiarize yourself with these rules, all these rules of differentiation, especially for like a test or an exam setting. You might not get all of the formulas on the question sheets, so you should always like know them, at least know some of them by heart. And you can always ask Dr. Mshlongo maybe what kind of formulas will be included, so you know which ones you have to memorize by heart. So I saw a hand raised. Can you ask the question?
So say, I want to ask if I will be wrong if I split ln x cube cos x all over root 1 plus 3x into ln x cube cos x minus ln into root 1 plus 3x.
Yeah,
Before I do that.
you can do that as well, but then you'll have to find now the derivative of two ln functions, right? You can do that. Okay, so that's the good thing about derivatives. So there's multiple ways, multiple rules that you can use to get to the same answer. So here we're just using one way, okay? Another way, like he said, you use the rules of logarithmic functions. You know that when you have ln of a over b, it's just ln of a minus ln of b. So it's basically ln of the numerator, right, minus ln of the denominator, which is square roots 1 plus 3. 1 plus 3x. So you can use this as well. Now, if you look for the derivative of this, you will see that you're finding the derivative of two separate ln functions, and then you're just subtracting them, right? So you can use the same ln rule that we have here for each one of these functions, and then you should be able, at the end of the day, to get to the same answer that we're getting. But I'm just using this way because I want to sort of practice all these individual rules for trigonometric for differentiation. I want to go through as many as I can, right? So we've seen the quotient rule here. There's the ln function rule, logarithmic function differentiation, and I'm sure we'll see as well the product rule. So I just want us to sort of practice all of this. So thus, if you substitute each of the values into our function that we have there, you have, right? So let me just copy this. You now have f of x prime is just the derivative of the numerator, right? So you have x cubed cos x prime multiplied by g of x, which is what is our g of x? Our g of x is root of 1 plus 3x, right? Which is multiplied by our f of x, which is again x cubed times cos x. So let's just rewrite that. Multiplied by our g of x prime, which is just g of x prime, which is just root of 1 plus 3x prime, right? Divided by whoever is sharing his screen right now, can you stop so I'm able to share? Right. Going back, you have g of x squared, so that's the root of 1 plus 3x squared, right? And as you simplify this, it's a long function. As you simplify this, now you have to find the derivative of x cubed times cos x. So let's try to find all of them separately and then just plug into the main function. So let's find this. What is the derivative of x cubed times cos x? Right, so as you can see, I'm breaking it down into small pieces so we can go through as many rules as we can. Here we have a product, so you use the product rule, right? Right, so the product rule tells us that if you have the derivative of the product of two functions, which is just a times b, right? It's equal to the derivative of the first function multiplied by the second function plus the first function multiplied by the derivative of the second function. Right, so that's the product rule. So if you apply it to our case here, is you get, what's the derivative of x cubed? Because our a here is x cubed. So what's the derivative of x cubed, guys?
3x.
Sorry?
3x squared.
3x squared. Thank you. So the derivative of x cubed is 3x squared multiplied by cos x, right, which is our b, plus x cubed, right, multiplied by the derivative of cos x. What's the derivative of cos x, guys?
Negative sin x.
Thank you. Negative sin x. Okay. And now this is equal to 3x squared times cos x minus x cubed times sine x. Can you guys just give me a minute? There's some interference on my side. Just give me a minute, guys. I'll be back. All right, guys, I'm sorry about that. Let's keep going. So next, we've simplified this. So now let's apply it to our root of 1 plus 3x. Okay, so let's copy again roots of 1 plus 3x. Right. And here again, you can apply the there's two ways you can do this. You can sort of memorize the rule for the square root, or you can use the rule, right? That when you have a function f of x, right? Let's say some function f of x, and you're trying to find its derivative, some function f of x which is to the exponents, let's say to some exponents n, and you're trying to find its derivative, what you do is you take down the n, so n, whatever that value is, multiplied by the derivative of the function f of x, multiplied by the same function f of x, but now to the exponent of n minus 1, right? And then, yeah, that's it, right? So this is the rule for some function, for a general rule for a function f of x. So in our case here, what is the value of n? If you look at root 1 plus 3x, what's the value of n?
1/2.
Thank you. So it's 1/2. So let's apply that to this case here. So 1/2. So now you have the 1/2 that comes down, right? Multiplied by the derivative of the function f of x, which is 1 plus 3x. And the derivative, what is the derivative of 1 plus 3x, guys? That's a question for you.
3.
3.
Thank you. So 3 multiplied by the function 1 plus 3x, right? To the exponent of n minus 1, which is just 1/2 minus 1, right? And we can simplify that to be now 3/2 multiplied by 1 plus 3x to the minus 1/2. Right? And of course, you can simplify this further to be 3 divided by 2 multiplied by the square root of 1 plus 3x. Okay, it's basically the same thing, right? So now we found our two values that we needed to plug into the original function here. So let's go back to that. So finally, or rather next, we have, if we, if we copy this, right? Now we plug in the values that we just got from our calculations. What we get is the derivative of x cubed times cos x. We substitute it with this whole thing that we found here. So let's open the brackets and put this in. okay, multiplied by root of 1 plus 3x minus x cubed times cos x multiplied by the derivative of root 1 plus 3x, which is equal to what? Which is equal to this whole thing here. Right? Divided by root of 1 plus 3x squared, which can also be simplified to just be equal to 1 plus 3x. Okay, so of course you guys can simplify this further, right? So you can simplify this further and see where it takes you. So I'll leave it as is. You guys can attempt the simplification as practice, right? So what I'll do is just to get our final answer, I'll just plug it, this whole thing that we found here, there, right? Divided by the denominator that we had there. So this is our final answer. Well, not really our final answer, but this is our answer. So you can simplify now, put to the same denominator in the numerator, and then try to simplify the square root of 1 plus 3x, divide. You can simplify this fraction here, okay, as exercise. So there's more that can be done here to make it look a little bit neater, because it's a bit messy right now. But basically, this is what your final your answer should be, right? Okay, any questions? Right. Okay, let's move on then. I'll do again. I'm wondering if it's worth it to do this one. Okay, you guys think, right? Based on this rule that I showed here, right, for f of x to the n, you can apply it to this problem, to question C here, question C and question B, right? You can apply that rule there and then solve that out. So let's try to do one question now in trigonometric functions, which is what we didn't really touch on, right? So for trigonometric functions, the rule says, right, if you have, or at least it's one of the rules, okay, it's more like the general form of the rule. If you have some function cos, for example, of f of x, right, and you're trying to find the derivative of that, what you do is, first you take the derivative of the inside function, right? Remember, we're always trying to go from inside to outside. Inside function, the derivative of that multiplied by the derivative of the outside function, which is cos. What's the derivative of cos, guys?
Negative sine x.
Negative sine. So we have negative sine of f of x in our case, not x. So negative sine of f of x, right? Multiplied by, yeah, that's it. So this is the rule, okay? So now let's apply it to this problem here that we have. If you apply the same rule to this problem here, what do we get? Well, we get Our f of x is now 3x squared plus 7. And what's the derivative of that, guys? 3x squared plus 7?
6x.
It should be 6x.
Yes. 6x multiplied by minus sine of f of x, which is just minus sine of 3x squared plus 7, right? And this should be simplified, just be equal to minus 6x multiplied by sine of 3x squared plus 7. And there you go. So that is it. That's your final answer. And yeah. Any questions? So yeah, especially for differentiation. So I'll tell you this because we sort of like moving away from limits now and going more into differentiation. It really is all about practicing. The more you practice solving problems and looking at different sort of exercises, the more, or rather the easier it will be for you, right? So it's all about practicing. So keep practicing with these problems. And like I said, you can apply this rule here. If you want, you can either take a screenshot or, but it's fine. You don't even have to because I'll be saving this for you guys. So you can apply this rule to B and C, right? We've done A, and A was like more like the most difficult one. And also for A, if you want to sort of practice your knowledge as well, you can try and use this form here of the question. So try to solve it going from here and then see if you get to the same final answer. You should be able to get to the same final answer. Of course, you can, like I said, you can simplify this answer again further to sort of get a more accurate and nice looking answer, right? Okay, so and then that's it. We've pretty much covered everything. And then for sub question, sorry, rather for question 3 and 4, we did them yesterday, but question 5 and 6 were like the most they looked like the most complicated one. So since we've done question 5 and 6 here, you guys should easily be able to do question 3 and 4, right? And for question 1, we're using the chain rule, the limits chain rule. So basically all you have to do is take the limits of what's inside here. So first you take the limits of 2tan inverse of x, and then you take the sign of that limit, right? So you take the sign, you take the limit inside the bracket of the sine function. And for question 2 here, you guys know this identity. The limit as x tends to positive infinity of 1 plus 1 over x to the x is just equal to e. Yes. Right? So you know this. So basically, what you have to do for B and C is just manipulate it in such a way that you have something that looks like it. And remember, for it to apply, for this rule to apply, you need to have the limit as x tends to positive infinity. You need to have 1 here plus 1 divided by, it could be x, it could be anything multiplied by x, any constant multiplied by x, but as long as it's in the exponent as well, right? As long as it's in the exponent as well, right? That's sort of like the general form. So all you have to do now is sort of manipulate each one of these limits to sort of get something that looks like that. So as long as the number that is next to x here in the numerator is the same number that's there, you can apply this rule. For example, if I just tell you, like for question B, you have 1 plus 1 over 2x, and you have 9 there. So how do you get 9 where the 2 is? What would you suggest?
It's going to be 2x times 9 over 2, I think.
Yeah, right. So you can do 2x times, so you can basically change this to 2x times, right? Sorry, just write it down like this. Times 9 over 2, right? Let me write it nicely. There you go. The exponent of 9 over 2, right? So that's basically in such that when you multiply in, you have 2x multiplied by 9 over 2, you just get the 9, the original 9 that was there. And then what you do is you take the limits inside the brackets, and immediately you can apply this function, this identity here. So you would have e here inside, e to the 9 over 2. So that should be your final answer. So same applies for this. You just have to multiply it. Sorry, you just have to manipulate it. Okay. So attempt that in your own time, and you should be able to easily solve this. Right.